Space Telescope Science Institute. Aida will give an introduction to the speaker now.
Yes. Thank you for being here today, Claus. So I first met Claus in 2009 as a postdoc at Space Telescope Science Institute, and so I'm really happy that he's able to give us this talk. Claus got his PhD in 1985 at Heidelberg University. He joined STSCI after 2 postdocs in 1988. So he's been working there for a while. And some of the responsibilities that he has had at STSCI are being in charge of HST telescope allocation process, the HST's director's discretionary time, the Hubble Fellowship Program, and the science policy evaluations. He has been president of IAU Division J, Galaxies and Cosmology, and chair of IAU's working group on massive stars. And he has been in the organizing committee member of IAU Commission 35. And he's been chair and panelist for NASA ADAP, Spitzer Space Telescope, the National Science Foundation, the Subaru Telescope. And well, his research interests are varied. Atmospheres and evolution of massive stars, population of massive stars, population synthesis. You may know that he is the main author of the population synthesis package, starburst 99, which is widely used in the world. He is also interested in young star clusters and H2 regions, star-forming galaxies, galaxy spectral energy distributions, and ultraviolet to near-infrared observations. So welcome, Claus.
Okay, thank you so much, Aida, for this wonderful introduction. And I mentioned it before, so this is a very busy week for me at Space Telescope. We have the JWST tag, and I should actually walk around virtually from panel to panel, but this is a very welcome diversion for me, this 1.5 hours. And of course, I would have loved to be in Mexico in person, and hopefully this will happen at some point further in the future. But at this point, it is all virtual. And so without further ado, let's talk about cosmic reionization and what we can learn in the local universe. Now, first, let me introduce to you my main collaborators in this project. Sanj Potharkur, who used to be at Johns Hopkins, Jim Heckman, Svea Hernandez, who is originally from Mexico, and she did her undergraduate at the University of Texas in Austin, then came to Space Telescope as a data analyst, then got her PhD in the Netherlands, and now she has joined STSCI as a staff astronomer. Then there's Janice Lee, Sally Uy, Roderick Overseer, and Bingqi Wang. And what I should do now is, because the right part is actually blocked for me here, and I just want to remove this here. Yeah, so now I can actually see my slides. All right, first a brief schematic of the Big Bang, and I try to find a figure that not everybody is actually showing. So hopefully most of you have not seen this one. All right, we all know the universe started with a bang, and for the first few 100,000 years, the universe was, I would call, foggy, because the photons were scattered by free electrons. And then after about 350, 400,000 years, the universe started to recombine. The free electrons recombined with hydrogen, also helium, and the color temperature of the universe dropped from prior to recombinations about 4,000 K, kind of orange, to something like 60K, pretty dark. And there was nothing actually to provide any photons. There were no stars, and nothing. And that's what we call the dark ages of the universe. And that lasted for several hundred million years. During that time, the first primordial stars appeared, some primordial black holes, and then possibly galaxies. And this was the period what we call reionization, which we think ended by about a redshift of, well, somewhere between 11 and 7. And then galaxies, as we know them, emerged, and star formation proceeded with a peak around redshift of 3 and 2. That's what we call cosmic noon. And then the star formation slowly petered out until now, where we are now. So that's a brief history of the universe. And the question, actually, the central question of my talk is, what causes the reionization? What are the sources that provided the ionizing photons that caused hydrogen and also helium actually to be reionized? And there are several suggestions. Some of the earlier suggestions or the more exotic suggestions, they're related to particle physics, some exotic decaying particles, or very early primordial black holes, or initial free primordial stars, population-free stars. But these are suggestions that are no longer strongly, actively pursued. And nowadays, the two leading contenders for reionization are active galactic nuclei or star-forming galaxies. And the jury is out, actually, which of the two are the prime agents of reionization. Yeah? So let's look at the properties of those two AGN or star-forming galaxies in a little bit more detail. And I'm using here a figure which is already 10 years old, but it may be a little bit outdated quantitatively, but it really shows what the problematic is. And that's why I love it's a little bit busy, and I will go through this in a couple of minutes for the non-experts. There are 4 quadrants here, and each quadrant refers to a different redshift. Redshift 5, 6, 7, and 8. And each quadrant at each redshift shows the required photon budget for the emitting sources to account for complete reionization, which would be here. So the goal is to reach 1. Then the sources would be able to reionize the universe. And the 2 sources that are shown here are AGN, gray shaded, and star-forming galaxies in 3 flavors. And essentially the x-axis here is a luminosity function. It tells you how many objects we expect to find as a function of brightness. And the dashed red line is essentially the observational limit. So it's a mixture of observations and extrapolations. And it shows you at a redshift of 5, AGN with large uncertainty, they might be able to account for reionization. And then there are 3 curves for star-forming galaxies. And that's for what we call 3 different assumptions on the photon escape fraction, F escape, as listed here, of 1%, 5%, and 20%. Of course, with star-forming galaxies, once we know that they are forming stars, we know that they are O stars. There's no question. But the question is, how many of these photons in the galaxy can actually leave the galaxy, can escape from the interstellar medium? And that's now shown for assumptions on 3 different escape fractions, 1%, 5, and 20. And you see at a redshift of 5, well, if the escape fraction is, say, let's assume 5%, under all likelihood, both AGN and star-forming galaxies would be able to account for recombination, for reionization. And then let's just go to, say, a higher redshift, redshift of 7, which is actually more relevant. And as far as we can tell, it will probably be harder for AGN to account for reionization. And then depending on what the escape fraction is of the galaxies, they might be able to account for reionization, or they might not. So this is the challenge. Okay, so to summarize, okay, we need about, if our assumption on the number counts of galaxies are correct and also supported by hydrodynamical models, we need about an escape fraction of 10 to 20% if star-forming galaxies at a redshift of, say, 7 or 8 are able to were able to reionize the universe. So it comes down to the question, what is the escape fraction? How can it be determined? And just to give you a flavor of actually of the challenge here, hydrogen is actually very, very effective in absorbing the ionizing photons. So an optical depth of 1 at the Lyman edge, short wave of 912, is already reached for a neutral hydrogen density, column density of about 10 to the 17. And that's very low. You know, essentially in almost all galaxies, star-forming galaxies, the actual column density along the line of sight is actually much, much higher. So if the universe, if the ISM were actually uniform, you would expect the effective escape fraction to be 0. Okay, so obviously you want to measure this, and you would say, well, let's just go to a redshift of 5 or 6 or 7, observe the galaxies there. There are many galaxies known, many star-forming galaxies, and let's just do a measurement. Well, not so fast. Of course, what's in between is the IGM. It's not only the ISM in the galaxies that have opacity, but also the intergalactic medium. And this is a plot which shows you the transmission of the intergalactic medium as a function of observed redshift of the galaxy. So again, let me be slow here and explain what we're seeing here. Let's assume you observe a star-forming galaxy at a redshift of 4. Then, of course, the Lyman continuum would be redshifted in the optical. That would be fine. But of course, intervening, if you observe this galaxy, you have absorbers at a redshift of 3.9, 3.8, 3.7, and so on and so on. These absorbers have Lyman Alpha, which is also very, very effective in absorbing. And this would show you what different Lyman Alpha lines then at a redshift 3.9, 3.8, and so on, would actually do with the radiation of the Z equal 4 galaxy. Original, you would be here, you could observe it, but then you get absorption. And then at some point you hit Lyman beta at all these redshifts, Lyman gamma, Lyman delta, and finally the Lyman limit itself. And then you can play this game for any galaxy which you observe the redshift of 3, 2, 5, or 6, and then you connect all the dots and you get the transmission curve of the IGM in the universe. And this tells you if you want to observe a galaxy at a redshift of 6, in order to measure the escaping radiation short of the Lyman break, essentially no chance, because you have no way of penetrating the intergalactic medium between the individual galaxies. So we cannot measure this. There's no observational test to do this. So what is plan B? The plan B is here. So this is our strategy, and this is what I'm going to talk about in the next 45 minutes. Okay, we are going to resort to local galaxies. We're trying to identify galaxies which we think are good counterparts of the distant galaxies and use them as training sets. Okay, so we find the galaxies. We try to find trends with galaxy properties. We try to detect the escaping photons, and then parameterize the escape fraction in terms of the accessible observed properties, like optical emission lines. Okay? And then we compare the local sample to the properties of the high redshift counterparts, and then we make predictions what we should expect for the ionizing luminosity at high redshift. Okay, so that's the work plan. So let's define our sample. And I would like to look at 3 representative redshifts. Between essentially no redshift at all, and of course you have to have a minimum redshift, because what you want to do is at the very least you need to redshift the local counterparts out of the Milky Way absorption, because our own Milky Way, the interstellar medium, absorbs the Lyman continuum, and we need at least a free velocity range of a few thousand kilometers per second in order to get out of the opacity of our own Milky Way. Okay, so this is the first redshift range would be about 0.02, 0.03, about 2 or 3%. So in other words, a few thousand or 10,000 kilometers per second. And the second group would be a redshift of 0.3. That's the range of typically what you observe in the Sloan survey. And then I'm very generous here. I also call this low redshift. So basically a redshift of 3. These are the kind of local of the Lyman break galaxies. By cosmological standards, I'm still considering these relatively local. And you can basically do a trade study. What are the pros and cons of these different groups? And let me go through this here. So of course, in terms of spatial resolution, spatial information, of course, you know much more about nearby galaxies, obviously. Now, in terms of solid angle, of course, you want to measure the escape fraction integrated over the whole galaxy, not just one star cluster that happens to be in your aperture. So that is better done actually by using a more distant sample. You also want to use ancillary data to the largest extent possible. Obviously, there are more data available for the local galaxies. Now, in terms of your sample, so typically the local galaxies are kind of hodgepodge, mixed bag. Oh, this galaxy is easy to observe. Oh, let's go for M33 or this one. Whereas it's much easier to define a homogeneous sample if you use one of the deep fields, like the Cosmos deep field or the Hubble ultra deep field. Okay, and then of course it's the question of the intervening IGM. Obviously, that's a clear pro for the nearby galaxies. And then, of course, there's the observational challenge. And I want to leave this one open. So let's look at these 3 groups here. And let's start with the nearby sample. And that's some work we did a few years ago. So this is now a sample at a redshift of 0.3, 0.4, corresponding to velocities of the order of 10, 15,000, which essentially buys you about 20, 30, 40 angstroms of access to the Lyman continuum that would not be blocked by our own Milky Way. So these are 3 galaxies, which by classification, they tend to be very luminous H2 galaxies. They have a relatively high star formation rate, so they are actually luminous. In terms of star formation rates, they're more like LIRGs, luminous infrared galaxies. And they're moderately metal poor. They're like kind of LMC-ish or SMC-ish. They have relatively low internal reddening by optical standards. Of course, by UV standards, that's still not negligible. So it's between 0.1 and 0.2. So these are these 3 galaxies which we observed. And currently, the only instrument that is able to do these observations is the cosmic origin spectrograph on board of the Hubble Space Telescope. So previously there were 2 other instruments that could be used. They are no longer in operation. It used to be some 15 years ago, FUSE, the Far Ultraviolet Spectroscopic Observer. This was an experiment led by Johns Hopkins, and and partners. And then in the 1990s, it was the Hopkins ultraviolet telescope, which was to a certain extent also able to do these kind of observations. But now it's really only COS, the Cosmic Origin Spectrograph. And this is a schematic which is a little bit blurry, and I apologize. And the spectrograph has two channels. One is the near infrared channel, and the other one is the far ultraviolet channel. Of interest here is the far ultraviolet channel. Light comes in here, entrance aperture, one reflection, grating, and here's the detector. Important thing here is there's only one reflection and there's no entrance window. That makes the spectrograph sensitive to radiation, to wavelengths down to 900 angstroms and even lower, but that has never been tested. Okay? So this is the only instrument where one can actually observe down to 912 angstroms. Okay? And so we use this instrument for these three galaxies, and that's what a typical spectrum looks like. And for the experts, there's some of the familiar lines. So this is a spectrum in the observed frame. So this is the carbon-4 line, which would normally be at 1550 angstroms, and you see it's redshifted here. It's a stellar wind line. And of course, if you notice, there's the broad Wolf-Rayet bump. So this is an actively star-forming young galaxy. There's nitrogen-5 stellar lines. There's oxygen-6 young stellar population. And if you look closely, this is the Lyman continuum, and there is something. Okay? So you can then use this spectrum. You can fit a model spectrum. You can use these stellar lines to essentially constrain the young stellar population, and then make a prediction of what the ionizing continuum would look like. Of course, the ionizing continuum is also responsible for the shape, for the profile of these spectral lines of carbon-4 and also of oxygen-5. And if you can reproduce those lines, that tells you should be able to reproduce, to make a reliable prediction of what should come out in the Lyman continuum. So this is now a close-up now in the rest frame of the Lyman continuum. And the heavy horizontal line here, this is the prediction for the level of the Lyman continuum that should be emitted if 100% of the radiation could leak out of the galaxy. In practice, you don't reach this. Essentially, 0 would be here. You only reach a fraction of this. Okay. Now you can measure actually. You go through reddening and everything, and you can also test different stellar models and so on and so on. And once you do that, you find the following for these three galaxies. This is now the escape fraction. First, just accounting for absorption by gas, which we call the relative escape fraction in percent, which is 22%, 21%, and here's an upper limit less than 60%. And then on top of that, you also have dust, which actually decreases the escape fraction because you have an additional absorption, which most likely you would not have in a primordial, in a high redshift galaxy, because there's very little or no dust. So there are detections, but this is really tough going. There are not so many galaxies where you can do that, which are bright enough and which have the right properties. So this was a very useful pilot experiment, but in the end, actually, that wouldn't give you the full answer. Now let's go to the opposite end of the redshift range explored here. Let's go to a redshift of around 3. And here's an example of one galaxy that was studied by Eros Mancella and collaborators, observed at ESO at the BLT. And this one is a redshift of 4. And for this one, they found a relative escape fraction of 60%. So these are the data. So if you're not convinced that there's really something, so this is the 2-dimensional spectrum, and clearly there is a there's a very clear detection. Okay? Now, there are so many galaxies, again, where you can do this. You can also try this with imaging. The problem is always what is called interlopers. Because once you observe the redshift of 4, chances are there are actually other galaxies very, very nearby which happen to be here. So this could also be, in principle, in this case it's not, a galaxy, say, at a redshift of 1 or 2, but not seen in the ultraviolet, but say in the optical or so, which just mimics the UV continuum, the ionizing continuum of that galaxy. And this was a trap, actually, many observers fell into early on when this was done like 10 years ago. Now we have a clearer picture, and there are actually maybe 10 or 20 or even more galaxies where this experiment has been successfully done. So it is useful, but again, it's tough going. Okay? And of course, let's recall this plot here. In principle, this is not really a clear measurement. It's a mixture of modeling and observing. But once, because if you observe at a redshift of 4, you still have to model the transmission of the intergalactic medium. And needless to say that this curve is the average curve for the universe, averaged over all sightlines. For a specific sightline, it can be much higher or much lower. So there's always the uncertain aspect of the properties of the IGM once you go to redshift of 3 and beyond. Again, it's kind of frustrating. So then let's go to the intermediate redshift of 0.3. And for this, we need to look at cos again, at the instrument properties. Okay, this is the effective area or sensitivity of cos between 900 and 1200 angstroms. Okay, this shows you various measurements of the sensitivity. Okay, the vertical bars here show you where the Lyman edge would be located for a galaxy at a redshift of 0.03, and that would be applied to the examples I showed you before, the 3 local galaxies we observed. So we were able basically to observe the Lyman continuum here in this window, where we have an effective area of only about 20 square centimeters. That's all you get. So typically UV detectors, these are photon counting systems. So they typically have quantum efficiencies of only typically 10 or 20% or so. No comparison with CCDs, which tend to have 60 or 70%, right? So you're in a much different regime here. Okay? However, once you go into this regime, and this is where you are, where you get when you look at a redshift of 0.3, then the Lyman edge would be here. And then you have a huge gain in sensitivity of cos. And that's a combination of detector properties and also of the grading properties. So if you can, pick a sample which is at higher redshift. Okay, and that of course also allows a very clean selection of candidate galaxies from the Sloan digital skies away. Now you would say, well, of course, if you go to higher redshift, your galaxies would be fainted. True, but this is more than compensated by the sensitivity gain. And again, actually twofold. It's not only the sensitivity, but you move away from the background noise. Okay, if you observe, and I'm going back here, in this range, you're heavily limited by the detector background, which is variable, unfortunately. Normally, in the far ultraviolet, you never worry about backgrounds. There's no sky background except in spectral lines, Lyman Alpha or so, and you usually don't worry about detector background because normally you're so far above and there's no readout noise. But here you are. So here you actually hit the detector background, which is very, very nasty, which is actually variable. It's actually determined by solar activity. For instance, if you have some radio noise, if the sun actually is active, which happens on time scale of weeks or months, then actually the detector noise varies. And it's very, very hard to constrain. So you really, really want to be up here. You can forget about the detector noise to a large extent. And of course, there are additional advantages. So the galaxies are farther away. You have the entire galaxy in your entrance aperture. It's easier to select a homogeneous sample. And if you're not happy with the galaxies, you can always refine your selection criteria once some certain trends emerge. And so this has been now an area that has been very actively pursued. And that's one example where I was involved with this, which was in 2014, where Sanj Kotarko had the lead. And this is a cross spectrum of Sloan galaxy. The data are in black. Superposed is a model spectrum in red. If you look at the data, you see the very strong stellar lines like oxygen 6. Here is nitrogen 5, which are very nicely reproduced by the models. Then there are also interstellar lines. There's plenty of them. There's silicon 2 line. There's an iron 2 line. Obviously, that's not in the models. And then there are lines like silicon 4 here, which is both a stellar line and which also has interstellar lines. But then you can actually, again, like before, use the model to make a prediction what the ionizing continuum look like, and you would actually compare this to the data. So this is now a zoom of the data, okay? And you see clearly there is something, there's a clear detection, and this is now a prediction of the models for different assumptions of the star formation history, for a different chemical composition. You can also do different IMFs or so. And so typically you predict that the ionizing continuum should be here, and that's what you observe. Then you compare the two, and in this case, you find a relative escape fraction of about 20%, which mean that if such a galaxy existed at a redshift of 6 or 7, and if they existed in large enough numbers, they would be able to reionize the universe. Again, neglecting dust, assuming there would be no dust in a high redshift primordial galaxy. All right, and there's now, you can always say, a whole industry. There are now tens of these galaxies, and there's one group in particular that's who are very active and also very successful in obtaining HST time. That's Yuri Isotov from Kiev and his collaborators. They have a large collaboration with the group in Geneva, with Daniel Scherer and Anne Berhan. And so I'm just showing you some examples. So typically, so this is now the Lyman continuum in the rest frame. Of course, it's noisy by itself, but you can bin, and clearly, once you bin that, you are clearly above 0. There are clear detections, and typically you find escape fractions of the order of between 10 and 20%. And so here's the current record holder in this sample. So this one has an escape fraction of 46%. Okay, and there are many more actually now. So we have very good statistics in the meantime in this redshift range, which now turns out actually the most successful and the best suited redshift range to address the question, what are the properties of Lyman leakers? All right, so I have now a smiley face, so let's focus on those galaxies. Okay, in some sense now, so it's not at the end of my talk, but this is essentially in some sense like a summary talk. So if there's anything you want to take away from my talk, so this summarizes it all. That's the message I would like to bring across. So these are the properties of local Lyman leakers. That's what we found by observing galaxies in the local universe, and these are the properties that are shared by all these galaxies. And I'm now going through all of them. So let's first talk about the morphology. So they all are highly compact. So these are galaxies or starbursts, star-forming regions. of sizes of the order of 100 parsecs, and they're very massive. Now, I should say our early observations were limited to these galaxies, but in the meantime, there are similar galaxies with masses down to 10 to the 8 to 10 to the 7, which is very, very important because then they come closer to the properties of what we believe are real primordial galaxies. So they tend to be not 10 to the 9, but they're less massive. So, but in the meantime, we also have less massive galaxies with very compact morphologies. Okay, but let's look at this sample, and again, that's from the sample of Yuri Isotov. These are the galaxies I showed you before with the UV spectra. Okay, these are now near UV images at 2300 angstroms. And so at first glance, you might say, oh, this looks like a star observed with HST when there was still spherical aberration. Or in the absence of that, you might think, oh, this is just a star cluster in a nearby galaxy. But this is the whole galaxy, okay? So they are resolved, but they're essentially extremely compact, almost looking like a point source, but they are actually resolved, okay? So the extreme compactness is responsible for generating very powerful outflows. And these outflows then disrupt the surrounding interstellar medium, and the idea is this generates channels that allows the ionizing photons to go unabsorbed out to the intergalactic medium and escape from the galaxies. So here's a summary of the properties of these galaxies. As I said before, they have masses of the order of 10 to the 9, but they're now less massive examples known, but they're as compact. They have enormous star formation rates, again, like in lurks, between 10 and 100 solar masses per year. And they're very, very compact, okay? So these galaxies, do I have the chemical composition here? I don't have it here, but then I should mention this. They are metal poor, but not super metal poor, so they're typically SMC-ish or somewhat below, but they're certainly not primordial. So they have metallicities of oxygen abundances of the order of say 7.8 or so. Okay. The next point, let's look at the emission line ratios of these galaxies. They have very high excitation radius and extreme values of R23 and O32. And let's look at this. Again, so these are two different samples observed with COS using two different nomenclatures here. And the left diagram shows the location in the typical diagnostic diagram and 2 over H alpha or 3 over H beta, where these galaxies are located. So this sample is more extreme. And here it shows the location where they are in the O32 over R23 diagram. Okay, so these are all confirmed Lyman leakers. They're very, very extreme. So if you want to select a sample of potential Lyman leakers, that's what you want to do. You want to look at very extreme ratios defined by O32 and R3 and R23. Okay, next one, interstellar absorption lines. Okay, the line strength of interstellar absorption lines, and these are typically the UV lines, carbon 2, sulfur 2, silicon 2, and so on and so on. They suggest that the interstellar medium is inhomogeneous, that they're whole. It's essentially a picket fence model. And let's look one galaxy, and this is a relatively nearby galaxy. It's Haro 11, and that's a famous galaxy because this was one of the strongest cases for Lyman continuum escape early in the life of fuse. And it was one of the test cases. At first, it was actually very heavily contested. There were some doubts about the dark and background subtraction, but these doubts have been laid to rest. So it's now considered a very firm case, and also confirmed with HST as a Lyman leaker. Okay, And so this is this region C, that's the region of the Lyman continuum escape. And this is now a cos spectrum again. And in this case, we don't want to look at the Lyman continuum. We want to look at the interstellar absorption lines. Okay? So these are typically narrow. So again, for reference, that there are stellar lines, there are the typical Cygni profiles, and so on and so on. But that's not what I want to look at right now. I want to look at the interstellar lines, and the interstellar lines intrinsic to this galaxy are labeled at the top. Okay? So in blue, and let's just use this one. This is the Silicon 2 line, which is at 1526. Okay? And all these lines are optically thick. These are extremely strong lines. There's absolutely no doubt that they're optically thick, but they do not reach zero intensity. Zero would be here. The same would be true for the Silicon 4 lines and all the other lines, the strong carbon 2 line, right? Now you might say, well, maybe it doesn't reach zero because you don't resolve the lines, and if you had higher resolution, it would. But the lines are actually resolved. Unfortunately, we have a very good test for that because we know what the line spread function is, because they're also Milky Way foreground absorption lines. And this is the corresponding carbon 2 line. So essentially, this is our line spread function, and compare the width of the line here and here, or you can do the same game with the Silicon 2 line here. It's here, and this is our line spread function. Clearly, it is resolved. They don't reach zero level. And you can also look at the ratio of the two Silicon 4 lines. If they were optically thin, they would behave like 2:1. That's the oscillator strength. But all the lines have the same strength, which suggests what you're not measuring actually is the oscillator strength. But essentially, you're measuring the covering factor. Okay, you can use this actually to measure what is the obscuration of the lines, and what's the fraction of the photons that can actually escape from the galaxy. Okay, and so this has been done. You find actually the covering factor is of the order of 40% or so, and we see this in many of these galaxies that are leakers, that the covering factor is much smaller than 1. It's a necessary condition. It's not a sufficient condition. There are also galaxies which have a covering factor of less than 1, and still they're not Lyman leakers. But it's one criterion among others. Okay. Next, let's look at Lyman Alpha. Lyman Alpha, the properties of Lyman Alpha can also be used to indicate the properties of the Lyman continuum. And for this, let's look at some models by Anne Verham. This was part of her thesis in Geneva some 5-6 years ago. And this shows you models for Lyman Alpha as a function of the optical depth and the structure of the surrounding interstellar medium of an ionizing cluster. Now, Lyman Alpha, in some sense, behaves very similar in terms of the absorption properties, very similar to the Lyman continuum, but it's also very different. So Lyman Alpha has also very, very high optical depth, even higher than the Lyman continuum, optical depth to ionizing photons. But there's one difference. Of course, it's a line transition, and it's a resonance line, and a photon will be resonantly scattered. It will be absorbed and will be re-emitted at a different direction, can go anywhere. And now, if the absorbing medium is homogeneous and static, it will be absorbed again and re-emitted again, and so on and so on. It can happily do this. In principle, if this happens often enough, then it might actually at some point escape from the H2 region and leave the galaxy. But unfortunately, there's also dust, and even the tiniest amounts of dust would actually be able to destroy these photons. It turns out that after a certain number of these scatterings, in, out, the photons are gone. So the photons only have a realistic chance to escape from the H2 region if there's a velocity gradient, so they can make it out of the H2 region relatively quickly before they are destroyed by dust grains. And there are essentially two ways for the photons to do this. Either they do this here, that they get scattered away from a velocity which is similar to the velocity of the original absorption, or they can also get scattered back and then back forth, where they would end up again with a different velocity that makes it, that enables it to escape from the H2 region. Essentially, you get this very characteristic double peak profile where you have the forward scattered and the back scattered photons, and depending on the velocity gradient and the amount of opacity in the center, you get a velocity shift, a velocity difference between the red and the blue peak. And you can actually use the velocity difference as a measure of the opacity in Lyman alpha. And it turns out the opacity in Lyman alpha scales very well with the opacity in the escape fraction in the Lyman continuum. And this is shown here, and in the meantime, there's an even better plot, but I think this one also shows. This is a sample of confirmed Lyman continuum leakers. So the escape fraction in the Lyman continuum is shown here. And this is the measured escape fraction in Lyman alpha. And you see, oops, there's a, come back. There's a very good correlation. Now this measurement is a little bit more involved, but it's an extremely powerful measurement to make a prediction. It's certainly easier to measure Lyman alpha than measuring the Lyman continuum. And finally, it's what we call the sulfur 2 deficiency, and that's something our group currently is pursuing. Using the strength of sulfur 2, the forbidden sulfur 2 line at 6730 for direct detection of a density bounded interstellar medium. Okay, what's the trick? So here's a schematic of an H2 region, and as you all know, in the Strömgren sphere inside here, so most of the sulfur is sulfur 3, and sulfur 2, which has an ionization potential of 10.4 eV, is actually formed just outside the boundary of the Strömgren sphere. And the idea here is, the trick is, if the Strömgren sphere, for instance here, becomes optically thin, density bounded, then the sulfur 2 is no longer sulfur 2, but becomes sulfur 3. And so we can measure the relative strength of sulfur 2 or the weakness as an indication of escaping radiation. And so this, just to put this on a little bit more quantitative footing. So these are models by Eric Pellegrini from his thesis. And it shows you the run of sulfur and oxygen in a typical H2 region. So there's a model H2 region, and it's a 1-star model. In the left, we have a model, it's a WM basic model with 38,000 K. This one is 43. Let's just at the left one, and let's just look at sulfur 2 plus, which is sulfur 3, and sulfur plus, which is sulfur 2. And it shows you in solid the run of sulfur 3, solid red, would be here. Essentially, that traces the Strömgren sphere. And then you have in dashed red sulfur 2, and it sees it goes up and up, it traces the outside. Note that this is a logarithmic plot which tends to basically pull things together. And in reality, basically, the contrast between the two is actually higher. So it's really, there's hardly anything in terms of sulfur 2 inside here, and really shows up here. So you can actually use this to to test whether any ionizing photons go out here, because then the sulfur 2 would also transform into sulfur 3. So this was a method which was proposed by us a few years ago. And by the way, so you wouldn't see actually that this doesn't work so well with oxygen. So this is the corresponding line for oxygen 3, which is here, and oxygen 2, which you have both in, both of them are actually in the H2 region. And of course, that's why you use oxygen 2 over oxygen 3 or the inverse in order to probe an H2 region. Okay. And so how does this work in practice? So this is a diagnostic diagram, sulfur lines, and it's the sum of the two lines over H alpha, and that's oxygen 3 over H beta, and you see this the typical star forming sequence, and the triangles, these are the Lyman leakers, and you see all of them are displaced to the left, away from where the bulk of the galaxies are. So that's very promising. And why is this promising? Well, you can actually do this relatively easily. So these are emission lines, which tend to be relatively strong. That's actually easier than doing absorption line spectroscopy, like with the interstellar absorption lines. And you can do this also with JWST. So if you do it with JWST, you can do the whole trick actually up to a redshift of Z = 6 and larger, okay? Because there are spectrographs that can actually do this. So this method actually has quite some potential now to extend this to higher redshift and identify Lyman leakers, okay? And just to remind you, and I'm just coming to my close here, just a look in the future. So this is it's the complement of instruments on JWST, and there are several spectrographs that would be able to do the job. They have resolving powers from a few hundred to a few thousand or so, and they go out to, depending on which kind of redshift you are interested in, you can do this with near spec to wavelengths of 5, even somewhat more than 5, close to 6, and then further out with MIRI. And of course, deep fields. And so these are multi-object spectrographs, and there are deep fields where you can do this. And just there's one example, for instance, this is the Subaru D Field, and it's shown here. And so that has, there are already optical spectroscopic data, which then at a redshift of 5 and 6 would actually probe the redshift ultraviolet, not the rest frame ultraviolet, not the near infrared or red what we want, but the ultraviolet. But so we know what the redshifts are, most of them. And so this field is here. So there about 50 or so star-forming galaxies have been identified. Most of them have spectroscopic redshifts. So we know where they are. And so these would be actually prime candidates. On all these galaxies, they have magnitudes of 25th, 26th magnitude, and that's really nothing for JWST. So essentially, within a few hours, you would get the whole thing and can measure the sulfur 2 lines and possibly get a shot on the properties of sulfur 2 and therefore make a prediction what the Lyman continuum escape in these galaxies are. So that's a look in the future. It has not yet been done. So all we need is, and I mentioned this before when I talked to you, here's our little thing, which will hopefully be launched later this year, and we are still on schedule. Launch is still scheduled for, we're still in October 2021, and then there will be the commissioning, and the first observations, scientific observations, should be executed sometime in mid-2022. So let's keep our fingers crossed. And I think I used up all my times, and I'm taking questions.
Yes, thank you very much, Klaus. It was a very interesting.
Should I stop sharing, or should I leave it on? What's better?
You can leave it there, and then yeah. So there is one question from Christoph.
Hi, Klaus. Very nice talk. Thanks a lot. It's very, very interesting. I was wondering about the sulfur 2. When sulfur 2 is decreased, it traces density-bounded nebula, and it doesn't correspond to the image you show of the leaking going through holes in the nebula. If there is holes, then the nebula will have S2, and there will be place where there is no nebula at all. So S2 will not be decreased. How do you take this into account?
You mean
two
in
kind
the
of leak.
nebula, or you mean outside?
Well, there is two way of leaking. Or you go through a nebula that is density banded, or you go through holes where there is no.
But we don't know which one does apply, right? So more likely it's the hole scenario. That's the more likely scenario, frankly. Yeah.
Well, in this case, S2 will not be decreased.
Yeah. So right now, I can only say it's an empirical result. So we find that in all the leakers where we have optical rest frame optical spectra, S2 is smaller than expected. So it's an empirical result.
Okay, so it points to density banded nebula, not whole.
Okay, that's a good point. All right.
Yeah.
Thank you.
Pepe, do you have a question?
Very nice talk, Klaus. It's a lot of work and probably really painful at the beginning, just to select the samples that you were describing. And I'm puzzled by this idea that the leaking might come through holes, because all these, at least in the compact galaxies that you were talking about, they are very compact, they are small, 100 parsecs and 10 to the 9 solar masses. That implies that you have a lot of concentrated mass there, about between 100 and 1,000 solar masses per cubic parsec, which is a lot of mass. And once that you form stars, the structure of the nebula has a density gradient, and you don't need holes, because the density gradient, if it goes like R to the -2 or something like that, that will provide you that the ionization front will leak out of the galaxy, especially in these small galaxies. So you don't need holes, just the density structure will do it by itself. Have you thought about that?
When I showed the models, you may have seen, actually, we always let the two possibilities stand. It's also the Lyman Alpha models. They look at the two scenarios, holes versus low density. At this point, we cannot really distinguish. On the other hand, the hole scenario, that has the advantage, or maybe this is wishful thinking, because the indicators I showed you, all by themselves, they're obviously not 100% foolproof. And the argument very often that is made is that this is non-isotropic. So why, say, oxygen 3 over oxygen 2 is not a unique indicator of escape, because the argument that has been made, not only by us, by others, is that, in some galaxies, we just look in one direction, and so there are holes, and the escaping radiation basically is leaking at this solid angle, and that's why it's not working. So that's why we keep this open. But I hear you, and I think we should be open to both possibilities. Also keep in mind that since these are relatively large regions, I mean, it's not a small star cluster like a few parsecs or so. So many of these regions may have had supernova explosions that may have pierced the interstellar medium. That's, of course, the other argument, that it's not a kind of, small star cluster, but it's an extended region that may have had individual supernovae, which may have pierced the interstellar medium. I don't know, but you may know this better than I do.
Yeah, well, yeah. If the these compact regions are flattened, then the leaking process and the holes with supernovae or with stellar winds will occur in one direction. You're going to end up having a lot of radiation coming out of the azimuthal regions.
Okay.
Good. Is there any other question? Aida?
Yeah. So Klaus, thank you for the very interesting talk. So transforming the observations of the sulfur-2 into an escape fraction is going to require modeling of both the ISM and the IGM, right? In order to be able to say whether the galaxies are able to reionize the universe.
Okay, but it's not IGM, right? I mean, so basically the IGM only comes into play shortward of Lyman Alpha, right? I mean, the IGM doesn't do anything to the sulfur-2 lines.
Right.
So the IGM, fortunately, that's not an issue, right? Now, and I should say also with the sulfur-2 lines, I'm actually surprised that Sylvia or Manuel did not jump on that. Of course, you still have to do some photonization models. Of course, sulfur-2 and sulfur-3, they have different chemical compositions and so on, different ionization parameters and so on and so on. So it's not so clear that at high redshift, at redshift of 6, basically sulfur-2 and sulfur-3 behave the same as in the local sample. That's an additional consideration. So obviously you have to be open and say that.
Yeah.
Oh, okay. So I guess I was thinking about the galaxies being in the era of reionization. Mm-hmm. And so my question is there any, is there going to be an effort to try to map the absorption of the IGM in more detail? It's going to be hard because you only have one JWST, but in order to understand better how reionization occurred.
Well, of course, this is, I mean, probably the redshift of 7, that's very hard, right? Because it's essentially completely opaque, right? Mm-hmm. So clearly, there are efforts that there's the whole group of people who do physics of IGM with quasar absorption lines, right? Clearly, they are trying to map this, but it becomes, once you go to redshift of 6 or 7, then you see that it becomes completely opaque or so. Yes, it is being done, and that's why we know actually that this is very, very hard, because this is really, it varies from one direction to another one, right? It will be very hard. It would be very expensive to do this empirically.
Okay, thanks.
Yeah, clearly there are efforts, yes. So the answer is yes. And what is the ionization state? What is the basically diffuse radiation field in the universe? Clearly, there are many efforts to do this. Clearly, this is non-trivial. Yes.
Okay, thanks.
Okay, one last question from Sylvia.
Klaus, I may have missed what you said, but what would be the proportion of these very compact galaxies that are leakers that would be necessary to reionize in a significant way?
Oh, well, we could, hold on. How do I get do I still share or not? Do I get
You're not sharing anymore.
But you can share.
Basically, we could go back. Well, let me just tell you. I mean, I sent you my presentation, right? You can feel free to send it around if you want. The figure I showed at the very beginning, the 4 quadrants, where I showed, the contribution at redshift 5, 6, or 7. Essentially, this is the luminosity function, and there you can actually see basically what you need. Essentially, you need many of these very low luminosity compact galaxies. And the absolute blue magnitude, the MB of those galaxies, I showed in the local universe. So these would be galaxies maybe with an MB of minus 16 or 17, and you can plug it into the luminosity function, then you would actually see where we are. We are not quite there yet, but we are getting the regime, right?
Okay, thank you.
Yeah, so they're less than the SMC, just to give you a flavor of that. So maybe 5 years ago, I would have said, well, it's more than the LMC. It's almost, like an L-star galaxy. But now we're getting further and further down or so. So now we are already getting in the regime where it's less than the SMC. It's not yet quite there, but we're approaching the regime.
So I mean, let me ask this very silly question. So then we assume that they are among the first ones that they were built because they were small.
Well, they're not primordial, right? They are already relatively metal rich, right?
Yes, yeah. The ones that you mentioned, they are already metal rich. But I mean, in general, in the way past at the early stages, do we need a lot of them?
You need a lot of them. You need because they're not very luminous, because at that redshift 7 or 8, the big galaxies have not yet been built up, right? They come later. So you need a lot of them because there are no big galaxies, right? There may be a few. Of course, now I have to be very careful. There are two schools of thought. So there's one school of thought, and I would say that's the majority, that you have a large number of not so luminous dust-free galaxies. And there's the other school of thought, and that would be Len Cowie and collaborators, who tell you, oh, there are a few very, very luminous, more than say 10 to 10, 11 or so, very dusty galaxy. And they have already been formed, and we just don't know about them because we don't see them. And there are a few examples. And so this is, I would say, it is still an open question, although the majority view is that it's actually many low luminosity galaxies, but I would still leave this open, and we should not be blind and keep the other option also a possibility. That would be my opinion.
Thank you. Okay, thank you very much again, Klaus, for this wonderful talk. I think this is the end, and see you everyone next week. Thank you.
Thanks a lot.
Thanks, everybody.
Thanks, Klaus. Take care.
Well, hopefully I can come in person at one point.
Oh, you will.
Okay.
Bye.